Okay, so I'm going to mute everyone out and ask Mark Sokol. We're going to go to Mark Sokol next and see what is going on in his neck of the woods.
Okay, so down here in New Jersey, we have a couple projects that we've been working on. First of all, last weekend we had 2 people staying over at the lab. Brad, I forgot his last name. He has he's on Twitter and Instagram as Sonic Gravity, and he was building this contraption. He tried to explain it to me. It's basically a whole bunch of wires on a disc, and it's supposed to spin around inside of this magnetic field and create these magnetic pulses. We hope to have him on at some point to explain exactly what it is, but I was pretty surprised at the level of workmanship that he was able to accomplish, and he was just using the lab for the resources, drills, and we just have a whole bunch of what's-its and whatnots that you probably need while you're in the middle of the project, and like running out to Home Depot half an hour versus you have it on the shelf right over there. So it was a great time saver for him. We also kind of feed off of each other's energy. So when you have people like that at the lab, pull 16-hour days or nights, and yeah, you just work yourself until you're dead. And I was also working on this project that Mike Gamble presented at APEC. You showed a picture of it. We worked on the gyro a little bit ago, and I just wanted to finish up the project finally. And we were just about done right when we started the conference, and then it turns out the last piece didn't fit properly. But basically, these are 2 3-inch gyros made out of brass. These were all machined on the CNC machine. I got them spinning at up to 15,000 RPM, pretty well balanced. The motors are literally inside it. They're outrunner motors that are stuck inside the brass. And these are the 3-phase wires. Motor controllers are like for RC cars. The whole thing without the battery weighs less than 3.5 pounds. And according to Mike's calculations, it should make around 1 to 2 pounds of thrust. So that would be very, very impressive if that actually works. We got grease bearings, and the servos are actually what create the thrust. They're supposed to put out 120 kilos per centimeter of torque. So hopefully we'll have this all up and running within the next day or so, and I'll be able to give you a demo of it. The next thing that I'm really excited about is our upcoming anniversary of APEC. And Tim mentioned it in the beginning. We want to do a hybrid conference with some people here in New Jersey in person. There's actually a 5-star restaurant across the street that we're going to have a buffet at. So if anyone wants to come down here, there's going to be a small nominal fee just to cover the food, and we'll probably have a couple experiments and demonstrations to show everyone live as well. I know a couple people are flying in. Aiden Schaefer, Jeremiah, and Sean Logan, I think, are going to be here. Jeremy's probably going to drive in as well. So we'll be sending out an email with more information, and we're just trying to gauge how many people are going to show up so we can know like what to expect. There are a couple hotels in the area if you have to stay overnight, and definitely recommend that. We work at the lab pretty late, so you come down, get your hands dirty, and see what it's about. Bring your own experiments. We can try them out inside the Faraday cage and show you what's going on. So
Mark, if I could jump in real quick, how can people get in touch with you if they want to come on November 13th?
For now, you can just respond to the invite email to APEC that goes straight back to my email. We will be sending out a feeler email for all the attendees through that same system, just to count how many people are going to RSVP. And we expect it to cost about $50 to $100 just to cover the food and some minor expenses, so nothing major. Again, the issue is the time in getting here in New Jersey.
Yeah, no, that's awesome. Sorry, I'm just flashing back to the last flight I went. Did I tell you? Last flight I went out, I got stranded in Dallas. So
yeah, you called me in Dallas, super pissed. Or right when you got back, I don't remember.
Yeah, no, it was right. I think it was right when I got back. Yeah, it was right when I got stranded in Dallas, So thank you, American Airlines. Little shout out to AA for not being able to manage their schedules there.
Well, if you can make it down to New Jersey, that would be amazing. But I know you mentioned you have other obligations, and for you, it's a
Yeah.
pretty long flight too.
Yeah, and then the work schedule and stuff. And I think for a lot of the folks in our audience, that's a challenge, right? You know, especially this time of the year, it's that post-pandemic recovery, but things are bouncing back.
Hey, don't give them excuses already.
So I mean, how are the other projects coming along?
There's a couple projects that are like kind of done, but I'm like afraid to turn them on without, some other experts or people that I feel understand it better than me next to it, because there's a lot of potential danger, especially with the new power supply we got for the Alzafon experiment. It's kind of hooked up and just needs a couple of wires and some safety measures, but that thing could kill a dozen elephants. So yeah, I really want to make sure that it's done properly and that the measurements are done well. And when Jeremiah comes down here, he's a calibration expert, so he'll be able to help with the calibration. And there's a couple other people that might be able to. I think Todd will be able to help with the transformer. So we need a couple of minds here just to figure out, make sure that we're not going to blow shit up before we turn it on, because a lot of these experiments you can just flick a switch and everything just goes shit.
Yeah, to get the impulse current from the klystrons, we're going to use the potential transformer because it has that ability as a potential transformer to supply like basically limitless current within the heat threshold of the transformer, which also comes with the side effect of it having no internal regulations or limits whatsoever. So it's unshunted, which means if you short it on the output, its input is effectively dead shorted too. And so it'll deliver as much power as it can eat from the lines. So there's that.
Well, so yeah, that was one thing I was going to ask. How are you guys getting around the limitations of wall power? I mean, you're on like the 220 circuit? And
This building is an industrial building. It's a 3-phase 208. So yeah, we're not in a garage. We're in it's an actual shop. The building used to be a printing press. So I think we have like 150 kilowatts service to the building. A lot of power here.
That's actually terrifying now that you mention it.
And to answer your question, Tim, using impulse power in terms of the inductance stored up in these systems are where we're getting the extra current from that's not immediately available from the line.
Oh, okay. Okay, I see what you mean. Store it in the magnetic field.
But we still need that continuous kind of CW feed to keep it at its bias.
Yeah, and we're talking about transforming that 208 up to like 12,000 volts at more than an amp for some of these klystrons. So that's a lot of freaking energy. If that shorts out, fireworks.
Yeah. So you have the inertial propulsion then, right? Which you were just showing us, and then
that could be done in a day or two. Yeah.
You've got the Alzafon thing, which is a continuing project, right? You guys keep working on that, and then. What about superconductor stuff? Are you guys still working on that, or?
Well, we don't have any plans on doing anything more with the superconductors, and we did want to do another replication of Podplanov, that impulse thing, but there's a lot of work involved in setting something like that up. You'd have to get vacuum chambers. Like if anyone's like super excited about that project and wants to come down here and help put it together, go for it. But like, we'll help you out. We got all the parts. The thing is just like the time and energy involved. Like even if it works, what are we going to do with it? Like you can't make a craft off of that technology.
Well, I can also add to that too, in terms of what we learned from Poor's papers and Pakhanov's writings. What we find is that we do need a very consistent crystalline structure of the superconductors, and the superconductors we can get off eBay or from other resources that are polycrystalline and highly unstructured, cracked, sheared, have all kinds of imperfections. Basically, they're not going to work as adjunction material. Plus, as we found out from Poor, you really need these type 1 and type 2 superconductors sandwiched together, so you get these energy transitions between the Cooper pair states as they jump from one set to the other. And then it's even ideal to send them through a attenuated insulator material, which could be anything using a Josephson junction. Basically, the great thing about superconductors, as we've learned, is that they will transfer their superconductive properties at supercooled temperatures to nearby materials. So say you have a fine sheet of copper, like a copper tape on top of the superconductor, it actually becomes superconductive in the near field of the superconductor, which is one of those strange properties about that near field effect. Cooper pairs can tunnel into the copper as well, but all these equal energy transitions And these energy transitions come with linear momentum. And when they suddenly jump band gaps like this, you get this extra momentum that's expelled out of the system, but we can't do it with the superconductors we have. And we would need some very specialized materials, some very hard to make superconductors requiring a multi-ton or several hundred-ton press that we don't have access to. So that's kind of the limitation. And we've already had several experts on APEC to talk about specifically the nature and importance of the monocrystalline superconductor structure when doing these gravitational experiments. So we kind of have admitted that we are not set up for that, and we're going to concentrate more on technologies that are more readily obtainable and stuff that we can do right now.
Awesome. Well, so I have some questions for you guys too. Let me let me go to Robert Gordon first.
I haven't really said much. What's the questions about?
I don't know, and then after that we'll go to open discussion. But let me go to Robert. Robert, go for it, sir.
Yeah. Mark?
Yep.
Hi. I'm around your neck of the woods. What part of New Jersey are you in?
We're in Hawthorne, New Jersey, which is near Patterson, like northern New Jersey.
Really?
Yeah, where are you?
Well, I'm personally in Massachusetts, but I've gone to visit family in Long Branch.
Oh, that's south of here. That's it's on the beach, right?
Yes, exactly. Yep.
Yeah, I know. I fly my paramotor down there sometimes.
Yeah, well, and if I mean, I'm in the Seattle area, right? West Coast is different. So Seattle to even San Francisco is like a long drive, right? Like 14 hours or something like that. But
no, he's talking like 2 hours probably. Like
that's what I'm thinking.
6
Massachusetts
hours,
to New
6
Jersey.
hours.
Yeah, I mean, Jeremy Riss is farther than you. He's in Rhode Island.
Jeremy Pott, is that how I pronounce your name?
Jeremy Riss, that's the YouTuber who's putting us on YouTube, Alien Scientist.
Jeremy runs the Alien Scientist channel on YouTube. He has, I think right now, about 110,000 subscribers. And then we broadcast an American Anti-Gravity. You know, Mark, I should also mention, for anybody who missed it, I'm re-rendering our footage in 4K. Obviously, it's not true 4K because that's not what our Zoom is. But like right now, the screen that I'm viewing here, where I can see you and I can see all the different people in it. And if somebody puts up a screen share, believe it or not, that kind of adds up to 4K. And so the re-renders they're not perfect, right? They're not going to look like the TV sets you see in Best Buy with but they are much nicer than the stuff that we've been putting up in the past. And that's all going up on the APEC channel. And I'm going to keep doing it until my MacBook dies. But
cool.
Yeah, those are hefty
you didn't
files.
get your new laptop yet?
No, I did get my new laptop, but it's been going 24/7. Those 4K conference files for our conference, believe it or not, I have some that are like 90 gigs.
Wow.
That's a 90 gig video file. Yeah. So I'm surprised YouTube hasn't shut me down yet. So, but they also take, just for anybody who ever does 4K, this kind of surprised me. It takes up to 5 days for one of those to render. I mean, not to render, but to convert once you upload it, right? Like with a 1080 file, usually those are ready in a few minutes, but with the 4K, it takes up to 5 days. So the technology is definitely not quite caught up with those files yet. They're massive.
But at least we'll be able to see every pimple on the presenter's face.
Well, they look nicer, right? They look nicer. And then the other thing that I'm doing is putting chapters in those. And I'm, for the time being, going to keep splitting them up because I've noticed that people share our various conference sessions, right? And so like with you discussing this, or like, Gary a few minutes ago when he was talking about MHD, people will actually take the YouTube of that, paste it into various places. So I want to keep doing that. But then for more of an archival thing, it's nice to just have the whole chunk there. And that chapters feature that YouTube just rolled out lets us split that up. So
cool. I see there's other 2 hands raised over here.
Yeah,
Carl.
yeah. Sorry, I nerd out on computers.
Oh, thanks, Mark.
No problem,
Thanks.
Robert.
I may want to come over and visit your lab someday.
We'd love to have you come down. What do you do, by the way?
I'm an engineer, mechanical engineer.
Oh,
But
perfect.
ever since the controversial non-conventional science engineer, I call it, I've been delving into electrical theories and all. So I've got questions for you and maybe Jeremiah Paul.
Oh, okay. We got lots of work for you too.
Oh, wonderful. I can commute from here. It's only 6 hours.
Oh, okay. That end of Massachusetts then.
Yeah.
Okay. Well, let me go to Harold next. Sir?
Yes, my question, Mark. The inertial device that you showed just now, if you test it in the vertical position, do you expect the thrust to be in the vertical, the horizontal, or both? What are you expecting?
I don't know. You should. We'll get back to that in a couple of days when I actually test it.
Okay.
This is Mike. I can answer that question.
Oh, there he is. He's the guy who can answer
Okay.
it. Mike, check this out.
Yeah, I know.
I guess horizontal.
You need to send a picture of that to Tom right away.
I want to send a picture when it's done. Like I still have to put the cap on.
Yeah, I was just gonna ask. Yeah, I was just gonna ask about
doesn't-
that. Yeah.
It doesn't fit. The hole was like, it's like 1/10 of a millimeter too
Yeah.
small. I have to drill it out a little bit more.
Yeah.
But this thing it's solid. It is
Yeah, I
really,
can see
really
that,
well
yes.
built.
It looks
Yes.
good.
Look, even I made this center bar in the shape of a hourglass, so it gives
Yeah.
space for the gyros to walk back and forth.
Yeah.
And everything is like press fit in, and there's screws that are countersunk everywhere. It's really, really well made.
So you
Um,
CNC'd this whole thing then?
Pretty much everything on it, including the gyros. And
If you
me and Mike went on a Zoom call together, designing the gyros, like air holes here and there, and everything needed to be taken into account because these things want to destroy themselves. So you got to be very careful with over engineering it.
if you can send me the dimensions of that, I can do a rough calculation on the force output.
Okay. You need the dimensions of the gyro, right? The gyro itself.
Well, the whole kit and caboodle, I need the center to center distances of the gyros, the diameters. You may have to put some lightning holes in that thing because it looks like it's going to be a little on the heavy side. Yeah.
Yeah, we could always do that. It altogether it weighs 3.2 pounds.
Yeah. Looks good from here.
Oh, and when I spun it up, it's like super smooth all the way up to 15,000 RPM.
Yeah.
And then you shut off the power and it's spinning like 10 minutes later, it's still spinning.
The big ones at Boeing would spin for almost a half a day unless you put the brakes on. You could reverse the winding motors like a slot car and put electronic brakes to slow them down. Otherwise, they'd spin forever. Those are 2-foot wheels.
Yeah, I mean, we'll get there someday. Right? The next size up is going to be the 4-inch.
Yeah.
I think these are like 4.5. So just to give you a size comparison, we're going from that to that.
Yeah.
I'm excited to try these, but I first want to perfect the smaller size. There's a lot of kinks to work out.
Yeah, you may have to put an offset in on those gyros a little bit. That's why I'm looking at the numbers.
Oh, okay.
Okay. Well, let me go to Carl next. Carl?
I'm sorry. Hey, that was awesome. Hey, hey, Mark, I had messaged a little while ago about the type 2 superconductor experiment you had done recently. Got a question for you.
Mhm.
So, all right, so you've got a circulating magnet, right? It spins. You've got a type 2 superconductor, super cold. You can quantum lock it. What would happen if you let go of that type 2 superconductor and you turned on the spin of the magnets?
It would just spin with the magnets.
It would move with the magnets.
Mhm.
Didn't expect that.
It depends. Like if it was quantumly locked with the magnets, then it would spin with them. If it wasn't quantumly locked with the magnets, it was quantumly locked to like regular ambient magnetic fields, it would probably just repel everything and just fly off to the side.
Yeah, I mean, I just keep on thinking about, you know, the virtual particles, Cooper pairs, and and yeah, I'm trying to imagine how they would respond if they were thrown. You know, like the thought experiment of like trying to play catch with these things using magnets, and you know, can you actually? Yeah, I didn't expect that it would move with the circuit. I thought it might, like, if it's not moving and you push it laterally along a ring of magnets, it would just, you know.
Yeah,
move. And I
that's
think,
those are different magnetic field lines. In that setup that I had, it was north south, north south, north south all the way through, versus so the magnetic field lines are sort of going in like a pie of pizza, and each one is a wedge that catches the superconductor and spins it around. Versus a rail setup, like I have one over here, it's north, north, and then south in the center. So it acts like a rail that, and the superconductor is locked in. It can't twist. It's locked in this direction, and it turns like that with the rail. So it has its north, north, and and south in the center, or the opposite of that. So it'll be north in the center and south on the sides that follow exactly the lines of the magnetic fields.
and so are you suggesting that if the track was set up differently,
It wouldn't run. Yeah.
it would stay stationary while the magnets spun? Okay, that's interesting, because that's what I expected. Is there any detectable lateral movement that you could think would be possible, or it's stuck, it's not going to move at all? Or is there a small, subtle possible movement that you could think would happen?
With what? With which setup?
The second setup.
You mean in a rail with south on either side and north in the center?
I think so, yeah.
It would just follow the rail, kind of like a train.
Okay.
Yeah.
Cool, man. Like, thanks for saying that. Like, I feel like I need to figure some stuff out before I ask you more questions.
Yeah, I mean, a superconductor kind of locks whatever magnetic field lines are present when it goes superconducting into its body. So like if you have a magnet here and the field lines are going like this, kind of like a donut, and you have the superconductor here, it's catching that angle of magnetic field lines. So in some configurations, if you caught it off on the side, it can wobble all the way around back and forth. It has like a weird axis of potential rotation, versus if it's smack in the center where everything is equal on either sides, it can spin around on top of the magnet. This is a single magnet because the magnetic field lines are the same donut shape all around. So it's able to spin around inside that vortex. When you add more magnets to the mix, the shapes start to change and you can get all different geometry. So you could theoretically create a jigsaw puzzle of magnets where you can't see anything in real life, but you can take a superconductor, quantum lock it in a certain spot, and then it would follow a track through the magnets, based on how you programmed it. It's pretty cool stuff that you can do. I've never seen that done, but that's a cool idea.
That is a cool idea. That's a cool idea. I want to talk about this more, but I don't want to take up any more time because
come down to the lab. We could do it.
Dude, I want to so much, man. I want to.
Well, let me go to Harold, and then after we go to Harold, let's do open discussion. I think you want to just do open discussion after that.
Sure.
Okay.
Yes, my question is for Mark about, I saw the video that you put about the blue boob experiment, how the magnet blew up completely. Can you describe what was the magnetic setup that you had there, that the magnet came out flying? Can you describe it?
Yeah, so that was I might even have that was pretty dangerous. We had 3 ceramic magnets placed inside of a 3D printed grid, and that had a center axis, and I was just spinning them up. They were all facing, it was all north facing away from the motor, I believe. And I set it up on the pendulum overhead. And I was aware that it might explode, which is why I was staying away from its plane of spin. And yeah, it came apart pretty quickly. There's a hole in the ceiling here.
You say centrifugal force only was the reason why it came out like that?
Well, centrifugal force is why it exploded, but before that, there was some movement.
Yeah, I saw it.
Yeah, it might have been just aligning with Earth's magnetic field, which in the lab it's facing this direction. So it would want to come out in this angle, which is what it was doing. That was the angle it was at when it exploded.
All right, thank you. That was an interesting experiment.
That was dangerous.
I don't know, an experience too. It's true, danger.
Okay.
Well, thank you. Keep
And the
them,
magnets survived it too.
Oh, really?
Ceramic magnets, they didn't break.
Oh, okay.
Well, so guys, let's do this then. I want to put it on gallery view. Everybody give Mark a hand. We do not clap enough for Mark.
No, shut up.
Well, no,
We don't clap enough for Tim.
No, I don't.
Yeah, let's give
I
a round of
Hey,
applause
I'll
for
second
Tim.
that.
Round of applause for
Thank you,
Tim.
guys,
You're doing
but-
good work.
There we go.
I always feel guilty about that because this time of the day, right? You get to the end of the day and it's like we're all kind of clapped out, and so then Mark comes on. Now, on the bright side, like later in the day, everybody's more mellow and relaxed, and so I think that's good. That's why I like doing lab stuff now, because and then there's less pressure too. It's not like you're always looking at your watch, but so yeah.